Hey guys, Jake here, coming at you with another math lesson today. Today I'm going to be going over the extreme value theorem, which just kind of builds on the extreme values that I was, kind of introduced in my last video, and then I'm going to keep talking about for the rest of this week, finding maximums and minimums. The extreme value theorem basically addresses the existence of an absolute maximum on a function. So I'm going to, kind of get into what it means and what it looks like on a graph, and then we'll continue building on this. Before I get into that though, if you haven't already, go check out my video from yesterday. I'll put a link up here and a link down in the description so you can start there if you haven't already seen that. But yeah, let's get into the extreme value theorem. So here's what the extreme value theorem says. Basically, if we have some continuous function, so we have a function that's continuous on a closed interval, it is important that it's closed. And let's just say it's whatever this closed interval is, a, b. Then we know that f has an absolute maximum and it has an absolute minimum for some x value within that closed interval. So it does need to be continuous and it does need to be a closed interval. This doesn't really tell us anything about a function that's not continuous or that we're looking for an absolute maximum or minimum on some interval that is not a closed interval. So for a function to be continuous, that essentially just means there's no like holes or jumps within that domain of a to b. And for it to be a closed interval, that basically means that these endpoints are included in our interval. If we have an open interval, so an open interval would be expressed with a parenthesis instead of a bracket, something like that. This is saying that a is not included in our interval, and an open interval does not apply to the extreme value theorem. The extreme value theorem does require a closed interval, so both endpoints need to be included in that interval. This extreme value theorem doesn't really tell us anything about actually finding the absolute maximum or minimum values. It just tells us that they exist. So there's going to be, some additional things that you would have to do to find what those values actually are. And I'll make a video about those. If you're watching this after I've already made those videos, I'll put a link up here so you can go check that out. But this theorem will at least tell us a way that we can easily figure out if those extreme values exist, and then we could go into finding what those values actually are another way. But what I want to do is kind of show you a couple examples that we could apply the extreme value theorem to say that the absolute maximum or minimum values do exist, and what that kind of looks like on a graph. So let's get into some examples. So let's start with this function here. You can see that we have our closed interval here. Here's a and here's b. Our function is defined within that entire closed interval, right? A and b are both included in our function. And not only that, but our function is continuous throughout this entire closed domain, right? We could draw this entire piece of this function from a to b without picking up our pen, without any jumps or holes. It is continuous on that entire domain. So based on the extreme value theorem, we know that there has to be an absolute maximum and an absolute minimum within this domain. So we can see that this is a case where we have our absolute minimum right here, right? This point is lower than all the other points on this function. This would be our d, the point where the absolute minimum is. And then we can see our absolute maximum would be right here, which just so happens to be on the endpoint. So it is possible that your global maximum or minimum would be one of these endpoints, either A or B, or it is possible that both endpoints are an absolute max or min. But you can see here, since we have this continuous on this whole closed interval, we know that there is a maximum and a minimum, a global maximum and minimum within that domain. So then similarly over here, we have another function that we could draw this entire function from A to B without ever picking up our pen, no holes, no jumps, anything like that. This function is continuous within the entire closed domain of A to B because both of these endpoints are included within that function. So we know based on the extreme value theorem that there must be an absolute maximum and an absolute minimum within the domain of A to B. And this example is interesting because we can see there's actually two absolute maximum values. Both C1 and C2, they have the same output, the same Y value. So f of C1 is actually equal to f of C2, and that's why these are both absolute maximum values. They both have the same output, same height, therefore they're both absolute maximums, and we have an absolute max at C1 and C2. And then we can also see that we have an absolute minimum here at D, because this point is lower than all the other points on this function between A and B. So this is two perfect examples of functions that are continuous within the whole closed domain of A to B, and therefore we can see that they do have absolute maximum and minimum values, and we can visually see what those are by looking at the graph. Like I said, there are methods to find absolute maximum and minimum values given a function, doing it algebraically and using calculus to find those. I'll make another video about that, and I'll put a link in the description of this video once that one is out, so you can check that out. But now what I want to show you is some examples where you can use the extreme value theorem to see that a function does not have an absolute maximum or minimum value. Or, at the very least, we can't use the extreme value theorem to say that it definitely does have one. Before I get into that section, though, if this all makes sense so far, go ahead and post a comment below saying, got it so far, so that I know you're kind of following along up to this point. Now I'll show you some examples that don't meet the criteria for the extreme value theorem. So starting with this function here on the left, we can see a graph of this function which is defined on the entire closed interval of 0 to 5. Considering our extreme value theorem, we needed a function to be continuous on an entire closed interval. This function is defined on that entire closed interval of 0 to 5 because it does have an output for every single x value between 0 and 5, and including 0 and 5. So we do have a closed interval here. However, this function is not continuous on that entire closed interval because we can see here there's a jump discontinuity, right? We have to pick up our pen to get from here to here as we're drawing this function. So this is not continuous on the entire closed interval. Therefore, the extreme value theorem does not tell us that this function must have an absolute max and an absolute min. In fact, we can see by looking at it, it does look like it has an absolute minimum, right? This point right here does look like the lowest point included within this function. But this function actually does not have an absolute maximum because this kind of portion of our function is going up and up and up. It seems like whatever's at the end of this would be the highest point, but this is actually an open hole. So this point right here is actually not included on our function. And as a result, there is no highest value that lies on our function that is higher than all the other outputs of this function, because having this be an open hole basically means that we can keep getting infinitely close to this point and we'll never actually reach that point. So as a result, there's always going to be some y value that we could get a little bit closer to where this ends without actually quite reaching it. And as a result, there's not one single output that's going to be higher than all the others. We could always get a little bit higher and a little bit closer to that open hole. So over here now we have something a little bit different. We can see this function has a vertical asymptote at x equals 0. So this function here, as we get infinitely close to x equals 0, this is just going to keep going up to positive infinity. So this function here is actually not continuous on the closed interval 0 to 5. It's only continuous on the open interval 0 to 5, right? It's continuous for all x values between 0 and 5, except not at 0 and not at 5, right? We have an open hole here, and then we have an asymptote at 0. So it's never quite going to reach 0, and it's never quite going to reach 5 right here. So therefore, this function is only continuous on an open interval and not a closed interval. So as a result, the extreme value theorem is not going to apply here, and it doesn't mean that we're going to have an absolute maximum and minimum within that domain. And in fact, we can see that if we're trying to find an absolute minimum value or an absolute maximum value, we're not going to be able to get one because no matter how close to zero we get, this function is going to go up to infinity. If we keep getting a little bit closer to zero, there's always going to be some output of our function that's a little bit higher to the left. And then same idea over here, same idea as what happened over here. As we keep getting closer and closer to 5, there's always going to be some value that's a little bit lower than whatever output we're at as we get closer and closer to that x value of 5. So this actually isn't going to have an absolute minimum or an absolute maximum within the domain 0 to 5. So like I said, the extreme value theorem really just tells us the existence of absolute maximum and minimum values. To actually find what those max and min values are, there's a little bit more that you'll have to do. And I'll make a video about that and post a link here so you can check that out. And a link down in the description as well.